contain a placeholder or a spot for every degree of freedom. And you add those together, and now you have a full structure degree of freedom, full structure stiffness matrix in global coordinates. And this is the solution procedure. So the overall equation remains the same. Nodal forces equals the total structure stiffness matrix, global stiffness matrix related to nodal displacements expressed in a global coordinate system. And we can split these horizontally, these equations. We'll have one bunch of equations that relates to those nodes where we know what the nodal force is. So in other words, this top equation relates to the non-support nodes, right? Any node that's not a support, we know in principle what the load is. We couldn't solve it otherwise. I mean, as engineers, we have to know what the loads are on our structure. And whereas this one relates to the support nodes. And we then split it this way as well, because in some of the nodes we know what the displacements are, namely the supports displacements, and some of the nodes we don't know what the displacements are. And if we split it in this way, and we look at the top equation, in principle, for this situation, not always, but in the vast majority of cases, where we know the displacements at supports, they will be zero. And therefore that disappears. And so you're left just with this. And that's a solvable equation, because we have the same number of equations as unknowns. They're simultaneous equations. The computer can solve that using Gaussian elimination or Gauss-Jordan elimination. And there's actually a couple of YouTube videos on Gauss-Jordan elimination. And once you've solved that, you now know what all the displacements are in the structure. And once you know that, you can now work out what the unknown reactions are. Because now you know that and that. So now you know all the reactions, all the nodal forces, and you now also can now go back to the element stiffness matrices, and you can calculate what's going on with the element. So we can go back in now, having solved for the global nodal forces and nodal displacements, and we can now go back in and back substitute and find out what are the forces in the member from the individual member stiffness matrices. And we did this example. Did we go through this example? I think we did. Perhaps we didn't finish it. Did we finish this example? I can't remember. That suggests we need to do it again, if you can't even remember if you did it. Okay, so what's he done here? Well, we've numbered the members, the nodes first, 1, 2, 3, and we've numbered the members. I'll make that a little bit bigger, sorry, I should go to the... There, it's easy to see. So we've numbered the nodes and we've numbered the members. And the next thing to do is to number the degrees of freedom. So we have 2 degrees of freedom at each end of each member as soon as we move into the global reference frame. So there are 6 degrees of freedom in all in this system, right? And you'll see he's got them numbered here, 1, 2, 3, 4, 5, 6. You start with the degrees of freedom whose values you do not know. You start with the nodal displacements whose values you do not know. So that will be all of the nodal displacements for nodes that are not supports, right? In this case, there is only one node that's not a support, therefore there's only 2 of the 6 degrees of freedom, displacement degrees of freedom, that you do not know. And it's number 1 and number 2. So we know what the force is at this point because we define it as the load on the structure. So the x degree of freedom. So that means that degree of freedom 1 is the x degree of freedom at the near end of the member, and degree of freedom 2 is the y degree of freedom at the near end. 3 and 4 are the x and y here, and 5 and 6 are the x and y here. He has them numbered on little arrows here. See, these little arrows are the degrees of freedom index. So he's got 1, he starts with x, then goes y, then goes x, then goes y, then goes x, then goes y. Alright? And we can fill in the vectors for the known part of these vectors. So displacement-wise, 3, 4, 5 and 6 are all 0 by definition of these being pin supports. And on the force side, 1 and 2 are 0 and minus 2. There's no x force, there's only a y force. Okay. So you fill these in, and you're starting from the top down here with the degrees of freedom where the displacement is unknown and the forces are known. And so the matrix splits this way, where the rows relate to the forces that are known, but the columns relate to displacements that are unknown. So you get known, unknown on the left with forces, and you get unknown, known on the right with displacements. You split the equation, and if you look at it, you'll see that all of these coefficients, they're going to end up getting multiplied, that by 0, that by 0, that by 0, and that by 0, yeah? Those 4 columns will multiply by those 4 rows in accordance with normal matrix multiplication. Therefore, you can see actually this is the only business end in the top 2 equations. All of that multiplied by all of that goes to 0. So that top set of equations reduces to that, yeah? Which enables us to solve for the 2 unknown displacements, and we have them here. And you know what, all the time he hasn't bothered to actually give a value, which isn't necessary when you're just teaching the method. Obviously, for the computer, you tell the computer. It only works in terms of explicit numbers. So now you have solved for the 2 displacements. And now we have here, this is these are, so now you take those values and you can use them now to solve. These are the 2 values, yeah? The bottom equation can now be solved. Let's go back here a sec. So the bottom, this bunch here is multiplied by these 2, see? Before we started, we didn't know what they were. Once we solved the top 2, we now know what these are. Again, all of these get multiplied by 0. So now the bottom equation, set of equations, can now be solved by multiplying this piece of the matrix by that bit of the vector, which gives us these 4. And that's what he's doing here. So from this, we can calculate these unknown nodal forces, which are here, otherwise known as support reactions. And when we do that, we get these 4 support reactions. So now we have everything we need, and the computer can now find out what is the force in each member locally. So The force in the member that you're looking for is an axial force. You don't, as an engineer, you don't want a computer telling you that the force in the member has an X component this and a Y component that. You want to know what the resultant force is in the member, yeah?